Okay, welcome everyone to this continuation of what is tropical linear algebra, tropical geometry, whatever you want to call it. So tropical linear algebra is tropical geometry, yeah. Tropical linear algebra is this idea of kind of having linear algebra in the tropicals, and it's usually related to some optimization, to some graphs, to some counting type problem. Yeah, so kind of a discrete version, if you want, of classical linear algebra. And yeah, one of the most important notions of classical linear algebra are determinants, and we'll see what they do in tropical geometry. But I start with a reminder on determinants. So determinants, I always like to think about these as the volume of a parallelogram or volume of some polytope. So you take the unit square, right? You transform it using whatever your matrix. This is your matrix. You want to know what the matrix is doing, and then you get some new shape, right? So it's kind of, this vector goes somewhere like here, this vector goes somewhere like here, and you get a new shape, right? Okay. And the determinant should usually be the area of this new shape, right? So the above, you transform the unit square into whatever type of shape, and whatever that polytope is, the area of that polytope should be measured by the determinant, right? And that's what the determinant is all about. Of course, the determinant has many, many more applications, but essentially that's what the determinant does. In higher dimensions, it's a bit more difficult to imagine, but it's like a parallelotop or whatever it's called, like many vectors that's spanning this rectangular type shape, and you want to know its volume, right? So that's the whole point of the determinant. It's almost what the determinant does, right? So there's this little sign involved. So here you can see the black vector goes here, or the black vector goes here, and the little angle between the black vector and the red vector is like positive or negative, and the determinant is really measuring that orientation change as well. So it's not just the area, but the absolute value of the determinant is the area. In tropical geometry, we take a log, so we don't really know what a sign is anyway. That will vanish, making tropical geometry again easier than classical geometry. But essentially, determinant is the area of this shape up to some orientation sign type thing that comes around. But we don't need the sign anyway. Oops, that was really bad. I don't want it to cross out the sign. So under log, we don't know signs, so we don't need any signs in tropical geometry. So here, the standard formula for the determinant, the sum over all permutations, and just the permutation that you just sum the elements, and depending on the number of crossings in the permutation, you put a sign. So if you have an odd number of crossings, like 1, you put a sign. If you have an even number of crossings, you put a plus sign. An odd number and an even number, and essentially you just do this type of operation on the determinant, right? Sum over all permutations, and you kind of permute the elements, the entry through, and take it up with a sign. Right? Sums goes over all permutations. And essentially there's no reason just to tropicalize that thing, right? So we just write a tropical sum here and a tropical times here, and that's exactly what the determinant is. As we said, we will ignore the sign, so it's really the tropical sum and a tropical product over the permutation type objects. So in formulas, sum over the permutations, all tropical now, product over the i's, ai, sigma I, where I is my tropical matrix. And if you really think this through, because sum turns into min, yeah, min over all permutations, and product turns into plus, this is really the minimum of these things, right? The minimum of all of them. That's the tropical determinant. And it looks way more like the permanent, if you know what a permanent is, because the permanent usually is exactly the same analog formula without the sign. And kind of the idea in classical linear algebra is that the permanent always counts something, and similarly the tropical determinant will count something. But note here again that this is somewhat much easier than the usual determinant. It's just the minimum over all of these things. And the permutation that realizes, or a permutation, there could be many, that realizes that minimum should play an important role. And it does. It's a certain optimization, solution to an optimization problem, as we're going to see now. But up to this point, really just you tropicalize the formula, strictly speaking, of the permanent, and what you get is the tropical determinant. So optimization again. So let's say you have a certain task. So, well, let's rephrase it like this. You have n workers assigned to n jobs, right? So you have an n by n matrix, and every entry records the training cost, let's say. So you could have something like 3, 2, 1, 0 or something, whatever. So worker, let's say workers are here, worker 1, worker 2, task I, task 2. So worker 1, if you want to train it for task I, you have training cost 2. If you want to train worker 1 for task 2, you have training cost 1, and so on. And the optimization problem is you want to assign workers to jobs such that the training cost is minimum. And there's a permutation, right? So here you have two options. You could either assign, you could either do it like that. Worker 1 gets job 1, worker 2 gets job 2. Or you can say worker 1 gets job 2 and worker 2 gets job 1. And you want to minimize the training cost, and the permutation that realizes the minimum of the tropical determinant is exactly the solution to that problem. So in that sense, all of these tropical notions will always encode some type of optimization problem. Here in this case, the supposed n workers must be assigned to n jobs type problem, right? I said again, the permutation realizing this minimum, or permutation, or any permutation, maybe that's how I should say it. Any permutation realizing this minimum will be a solution to this type of problem. So that's what the tropical determinant is. It's really just take the tropical analog of the determinant formula. You lose this idea of having volume, and you lose the idea of having orientation, but you gain something new. And in this case, the new thing is you have a combinatorial object, right? It's some type of optimization problem that you are trying to solve, and that you're actually solving with the tropical determinant. Anyway, I hope you enjoyed this video, and I also hope to see you next time.